And then you're going to ask me the next question. I always get this question. If there are such parallel universes, then is Elvis Presley still alive in one of these parallel universes? Well, yeah. You can write down the equations to create a universe where Elvis Presley is still belting out hits, but in another universe. This is how crazy this theory is. The only thing going for it, like inflation theory, is that it fits the data. Inflation theory, which postulates a multiverse of universes, is consistent with all the data. Now, you talk to a kid and they say, I know all about that. I watch comics. I mean, I see the movies. And in the latest Avenger movies, guess what? The whole plot takes place in the multiverse, which is what I do for a living. I work on string theory, and in string theory is defined in the multiverse. So even children have caught up with us.
But this is see what intrigues me as well is what you see, because talking to different physicists, some physicists when I talk to them say they see equations when they talk about 11 dimensions, and others seems and in the book you mentioned Richard Feynman a few times, and some people say he had synesthesia, and that was one of the things which seemed that he could make these incredible leaps. Almost a leap where he had to do the working out afterwards, get to the answer, and then go. Now I'll find out how I. And so when you're thinking about those ideas, when you're thinking of string theory, when you think about parallel universes, what are you seeing in your mind at that point?
Well, evolution has given us a brain by which we can visualize three-dimensional tigers and three-dimensional bears, and we can avoid them. However, our brain does not understand five-dimensional bears or six-dimensional tigers because they don't threaten us. No six-dimensional tiger has ever jumped on me, so evolution did not give me the ability to visualize these higher dimensions. So that's a problem. But artists have been fascinated by the fact that three is not a special number. Three dimensions is not special. Salvador Dali was fascinated by the fourth spatial dimension. He even drew Jesus Christ crucified in the fourth dimension. Go to Google and look up the painting, very famous painting, Hypercubicus Crucifixion, Jesus Christ crucified in the fourth dimension. And then when Salvador Dali had melted clocks, that was his trademark, right? Melted clocks. What was he doing? He was trying to represent the fourth dimension of time on a two-dimensional canvas. Now, how do I know that? Because he would spend time at Brown University talking to the mathematicians there. And the mathematicians say, yes, they entertained Salvador Dali on a number of occasions, stayed over at their house, in fact, and he pumped them for all the information. How do you visualize a higher dimensional being, a higher dimensional world on a two-dimensional canvas? The answer, surrealism. Now, maybe you saw the movie Interstellar, starring Matthew McConaughey. That was a big budget Hollywood movie. At the end of the movie, Matthew McConaughey is thrown into a time machine. And where is he flown into? The fourth dimension. He's thrown into a tesseract. That's the final scene of the movie that many people are puzzled about. Why is Matthew McConaughey floating in a cube? He's actually floating in a four-dimensional cube because string theory is defined not just in 4 dimensions, but in 10 and 11-dimensional hyperspace. So you see, even the comic books are beginning to catch up to theoretical physics.
I mean, this seems a very important thing as well, which is, I remember talking to Sean Carroll, I think the first time I met him, and he'd been working in Hollywood on the film Thor, and his job had been to make sure that the gods from Asgard, that the wormhole they used was as accurate as possible, which I loved. The fact that you're dealing both with fictional gods, Norse gods, but you still want the wormhole to be as accurate as current understanding allows. Now, that seems to me to give, and also with the work of Christopher Nolan, this tremendous hope that if we put these things in pop culture and people hear the words, they might just hear this term here and tesseract there, then it starts to become something that people aren't scared of, because it does. I don't know how you feel, but it feels to me in the last 20 years, we're beginning to see a lowering of the fear of physics.
Yes, in fact, it was in the last century, in the 1800s, there was a Victorian mathematician at Oxford University by the name of Charles Dodgson. And he knew about these wormholes. Mathematicians call them multiply connected spaces. If I have two sheets of paper and I drill a hole between them, that's called a multiply connected space. Physicists call them wormholes. Mathematicians call them multiply connected space. So Charles Dodson, being a professor at Oxford, wanted to write a children's book about this. He couldn't do that under his own name, so he created a pseudonym, Lewis Carroll. And that book became Alice in Wonderland's Through the Looking Glass. The looking glass is the wormhole. This is the first representation of a wormhole in the English language. Alice in Wonderland has a wormhole. If I take a black hole, for example, and I spin it rapidly, it doesn't collapse to a dot at all. It collapses to a ring of neutrons. And if you fall through the ring, you go through the looking glass into a parallel universe. Now, of course, this is pure mathematics. No one has ever done this before. I don't advise you to do this. But there's a theory that says if you fall through the ring, you wind up in a white hole at the other end of a black hole. And we've looked for them. This is serious physics. We have looked for white holes in the universe. So far, we have found nothing. But hey, there could be a white hole on the other end of a black hole. Stephen Hawking wrote many articles about the stability of these wormholes and said they could be used for time machines and for faster than light travel. He eventually concluded that a wormhole through space may be possible. Time he had doubts about, but yeah, a device that goes faster than the speed of light through a wormhole may be physically realizable, said the late Stephen Hawking.
Now, I wanted to, as I mentioned before, you mentioned Feynman a few times in this book, and Richard Feynman, at one point you mentioned him when he said that he believes it's true to say that no one understands quantum mechanics. Now, that was 60 years ago. What has changed? In terms of our understanding this incredibly counter-instinctual world, how much has changed since 60 years ago when Richard Feynman said that?
Well, there are two great interpretations of the cat problem. The cat, the Schrodinger cat, is one of the greatest paradoxes of all time. If you can resolve the cat problem, you will win the Nobel Prize in Physics. So if any of your listeners ever figure out the cat problem, I have a word of advice. Tell me first. Tell me first, we'll publish together, and we'll share the Nobel Prize. The cat problem is very simple. You put a cat in a box. Attached to the cat, there's a gun. A gun is connected to uranium. Uranium firing is a quantum event. When the uranium atom fires, it sets off the gun kills the cat. So is the cat dead or alive? Well, according to quantum mechanics, and this freaks people out, before you open the box, the cat is neither dead nor alive. This is how I teach quantum mechanics. I teach students, I go to the blackboard, and I write the wave function of a dead cat, and I add it to the wave function of a live cat. At that point, the students all start to shake their heads, go like this, because how could you be dead and alive simultaneously? Now, how do you resolve whether or not the cat is dead or alive? You open the box. You have to make a measurement. But before you open the box, the cat is both dead and alive. Now, if you don't like this, get used to it. This is the universe. The universe doesn't care about your common sense. If your common sense feels violated by being dead and alive simultaneously, tough. That's just the way the universe is. Because that could be an electron. An electron spin up, added to electron spin down. And what does that give you? Modern electronics, the internet, laser beams, the wonders of quantum theory in your living room is all based on the idea that electrons can be here and there simultaneously. Electrons can be two places at the same time. Now that freaks people out. Einstein hated this idea. Einstein would invite guests to his house in Princeton, and he would say, look at the moon. Does the moon exist when a mouse looks at the moon? I mean, it's crazy. It's bizarre. But like I said, get used to it. That's just the way the world is. Einstein was wrong in this one. The world really is quantum mechanical. And that's one reason why it's so difficult to marry this bizarre theory called the quantum theory with relativity. which is based on smooth manifolds, smooth trampoline nets, curved space-time, beautiful, elegant, while matter is based on the cat problem. And again, if you can ever figure out the cat problem, you'll be recognized as the next Einstein.
So I'm one of the things that because I love reading books like yours, and then sometimes I stop and I think, why am I doing this? Why do I need to know these things? And you must sometimes, when you're writing the books, thinking, what do we need to know? Those of us who are non-scientists, who are drawn to this world, and then think, well, we're never really going to fully understand the equations. There's always going to perhaps be a limit of our comprehension. What is the drive to get people to become aware of some of these ideas, which can seem so arcane?
Well, I think the universe is a chess game, and there's a destiny. We humans have a destiny, and after 2,000 years, we finally figure out how the pawns move, how the bishops move, and how the knights move. One day we will have the God equation, and we'll understand how the entire game moves, and then we'll become grandmasters of the chess game that we call the universe. And then people come up to me and say, Professor, aren't you putting yourself out of a job? Aren't you going to be on the unemployment line, begging, looking for pennies with your cup? Because you're going to be out of a job. Physics will end. This is the end of physics. No, I don't think so. It's the end of learning the rules of chess. That's all. We are not grandmasters yet. We don't know how to manipulate space and time. And, well, perhaps a civilization in outer space, millions of years ahead of us, aliens in outer space, perhaps they've already mastered this technology. Perhaps they are grandmasters. But we're still in the process of figuring out how pawns move, how the knights move, figuring out the rules of the game. So therefore, I think humanity has a destiny. That is our destiny, to figure out the rules of cosmic chess.
And wonder, are there any particular ideas of physics which you have found yourself resistant to when you first heard them? Have the ones that have stayed with you for longer that you've really had to battle to accept?
Well, no. I mean, string theory has so many surprises that I have to keep an open mind. I like to think of it as walking through the desert of Egypt, and you stumble upon a tiny pebble, and you brush away the sand, and you find that it's actually the tip of a pyramid. And over the decades, you excavate the pyramid, and you find strange hieroglyphics, strange animals, strange drawings on the side of the pyramid. Finally, after many decades of hard work, you're finally at the ground floor. The ground floor of this enormous pyramid with mysterious hieroglyphics and etchings and diagrams. And we're about to open the door. That's where we are today. And I think this result, outside Fermilab, outside Chicago, outside Geneva, Switzerland, could help us to open the door, because this pyramid indicates that it's smarter than we are. We were not supposed to see this theory. This theory was discovered by accident. Accident. We were not supposed to see this theory for perhaps another 100 years. But here we are, witnessing the birth of a crazy theory. Who would have thought? String theory vibrating in 11-dimensional hyperspace? I mean, who would have thought that something so bizarre, so crazy, may be the secret to why this pyramid actually works? But of course, we have to test it. And that's why this new result out of the Large Hadron Collider is so interesting. Is this the first testable prediction of the theory? Well, stay tuned and we'll see.
Now, I just want to ask you, we're just about to, we'll take questions from the audience, and I know some of them are coming in now, but please do send if you anything you'd like to ask Michio. But one of the things that I often wonder is some people do see the how and the why questions as being entirely separate. And there are those who see science may well help us, our physical being, but in terms of Wittgenstein talked about the idea that we might, in the end, understand all the secrets of the universe, but all of the problems of living remain and are untouched by understanding the science. How do you feel about that?
Well, I like to quote Galileo. Galileo once said centuries ago that the purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So, in other words, science is about natural law, about how the heavens go. But religion is about ethics, how to go to heaven, how to be a good person, how to treat your neighbors well, how to go to heaven. The problem occurs when people who are natural scientists begin to pontificate about natural law, about ethics. Or we have problems when ethicists in religion begin to pontificate about natural law. As long as we keep these two realms separate, they are complementary. I see no difference, no contradiction between religion and science as long as they keep their domains intact. And we don't confuse the mission of religion and science. I don't see any problem at all.
Well, that brings us very neatly to our first audience question, which is from Ben. And Ben would like to know, he says, you've described yourself as an agnostic. Have your studies ever seen you sway closer or further away from a God as a designer of everything?
Well, I believe in the God of Einstein. Einstein did not believe in a personal God that answers prayers, that smites the Philistine, that walks on water, that does all these marvelous things, especially at Christmas time. I don't believe in a personal God. I believe in the God of Spinoza and Einstein, the God of order, simplicity, harmony, elegance. The universe could have been ugly. The universe could have been random. The universe could have been chaotic. It could have been a mist of subatomic particles with no consciousness, no beings. It could have been that universe. But our universe is gorgeous. It's incredible. You realize that on one sheet of paper, we can put the theory of almost everything. Einstein's equation, the standard model, as ugly as it is, can also fit on a sheet of paper. It didn't have to be that way. And yet here we are contemplating the fact that there could be a master equation 1 inch long that summarizes the standard model and the quantum theory. It didn't have to be that way. So Einstein thought of himself as a child opening the door to this huge library. This library containing all the secrets of the universe, and all he could do as a mortal was open the first book, first page, first paragraph. That's where we are today. The mystery of the universe is before us. And that was his conception of how we begin to understand the theory of everything, the God equation, the equation that makes this library possible.
I love it. There was Carlos Frank, who's a cosmologist up in Durham and does believe in a religious God. And I have lovely conversations with him because I think it's not the same as a lot of other people's religious God. He says he sees God as starting the universe and then going on holiday. I said, I'm sure a lot of the other people in the churches aren't seeing God that's been on holiday for that length of time. But I rather like that idea. This is from Julie, who would like to know, how do you wear the moniker of celebrity physicist or public scientist? Is it a burden or a privilege? Would you rather be in the lab more often?
Well, I'm a theoretical physicist, and people ask me, what do you do for a hobby? Well, I like to do theoretical physics. It is my hobby, but it's also my avocation. And so that's pretty much what I do for a living. Now, I realize that if you are a public figure, there's a purpose behind that. And that is you want to educate the public to the possibilities of science, because where does wealth come from? All this wealth that we see around us. Some people say, politicians say, that wealth comes from taxes. But taxes simply rearrange wealth. You rob Peter to pay Paul. Economists say that wealth comes from printing money. But that simply means that you have to pay interest on your great-grandchildren's investments. That doesn't mean that's a source of wealth. I say that we scientists have to tell the people that wealth comes from science and technology.